Okay, we're back here, and the equation that you saw here has a constant mu naught that has a value 4 pi times 10 to the minus 7 Tesla meter per ampere, and it's called the permeability constant. Okay, and try to remember this law, memorize this law. It's rather easy to remember. Okay, remember it's going to be directly proportional to the source of magnetic field, which is the current, and inversely proportional to the square of the distance, right? Then you have this cross product here upstairs and this constant mu naught over 4 pi. Okay, so there is another way of rewriting this equation instead of a simpler way, by the way, if you write that in terms of an integral, okay? So, which is called the Ampere's law. B field here, B field here, ds, mu naught, I. Okay, so let's write that down. So here you go. So let's take a look at the laws so far, in integral form, right? Laws of electricity and magnetism. Laws of electricity and magnetism so far. Okay, the first one that we saw was the Gauss law. Here you go. E dot, I don't like this dot. E dot dA, remember that? E dot dA. Here you go. And then we have an integral here. And it's an integral over a closed surface. Go this integral right in here. Okay, and what goes on the right side? It goes, you have Q enclosed over epsilon naught, right? Epsilon. Here you go. That's the law. The first law, that's Gauss's law. Then we also have the law that states that we do not have any magnetic monopole. Both of them are surface integrals. And now we have this law here, Biot-Savart law, that can be here written in integral form. And the way you write that in integral form is the following. B dot ds mu naught I. Mu naught I. Okay. Now, of course, you have that other law too, the magnetic force law that you saw. I'm not going to put it here. Similar to Biot-Savart law. That's Ampere's law. Biot-Savart law the last integral, is Ampere's law. Ampere's law, which is the integral, uh, format of the Biot-Savart law. We have okay, so here you go. What we're going to do now, we're going to calculate magnetic field at the center of a loop of radius A and current I. Okay, and we are going to use Biot-Savart law to do that. Here we go. Current I, radius R, or radius A. Okay, so take a look here. At the center of the very loop, we have current in this direction. We gotta cross ds with R. The magnetic field must be upwards. Okay, so let's do this calculation. You know, some problems you use the Biot-Savart law, some other problems you use the Ampere's law to calculate the magnetic field, okay? So here you go, goes like that. Okay, so here you go. ds cross r hat is going to be ds in the z direction. In the z direction. Because we're calculating at the very center of the loop, you know, every point along the loop is going to have the same distance, a. So we can replace r with a. And then we have to come up with an integral now to calculate this equation here. Okay, so here we go. Here we go. We take everything that's constant outside. Even the a square. And we are left with the s. Oops. Okay. The s is going to be 2 pi a. That's a simple problem. Okay, but we can have more complicated ones. I'm going to cancel out a and pi and 2. A and pi 2. Okay. That's the magnetic field there at the center of the loop. U naught I over 2a. Which is the same. Here you go. Now what about along the z-axis? Okay, you have to visualize as well. Here you go, along the z-axis. We have this ds cross r, and the dB is gonna make an angle. When you integrate all over the loop, you're going to generate a magnetic field that's going to be a cone. And the field components in the xy axis are going to cancel out. Okay? So it's a question of find out what's this angle here of the magnetic field. Okay? Okay, notice that dB and R vectors, they are perpendicular to each other. Okay, here we go. So this angle here should be this angle here. Okay, so here you go. Alpha plus 90 plus beta is equal to 180. You gotta visualize that. That's the geometry problem. Okay, beta plus 90 plus this angle here should be 180 as well. Okay, so this angle here should be equal to this one. Okay, so, see, let's do it again. This angle x, let's call this angle x, plus 90 plus, I'll call this angle here beta, should be 180. Beta plus 90 plus this angle should be 180 as well. So this angle here must be equal to this angle here. Okay, so beta was repeated in this case here and in this triangle. 90 degrees as well. 90 degrees here, 90 degrees here. Okay, so now this angle here is going to be what? The cosine of this angle is going to be A over R, angle X. Okay, so the looking at the figure, now repeat this calculation for any point along the z-axis. Okay, note that dB makes an angle x that we have to calculate. Okay, so this angle x, makes an angle x with the z-axis that we have to calculate. This angle x plus pi over 2 plus an angle that I'm going to call beta is going to be equal to pi. Okay? This is not a triangle. Let's go back to the drawing. This is a, my angle x, right? Yeah. This angle must be pi over 2 because the dB is going to be perpendicular to R, simultaneously perpendicular to R and ds. So x plus pi over 2 plus this angle here that I'm going to call beta, goes 180 degrees. Now I'm going to get another equation for a different, for this triangle here. I'm going to get an equation for this triangle here. What's going to be? Beta, okay, I call that beta, right? Plus 90 plus whatever, okay? I'm going to write that down here. using the right angle triangle formed by the z-axis, the r vector, and the radial and the negative radial direction, we have, okay, we have the first one that we are going to mention is going to be the beta. Let's put that in the proper order, right? Beta plus pi over 2. Right? Beta plus pi over 2 plus whatever. I'm not gonna call that. I'm not gonna call that x. I'm gonna call that y. Okay? And that's gonna be equal to x. So it's gonna be equal to pi. I'm gonna solve for x and I'm gonna solve for y. When we solve for x and solve for y, we notice that those equations are similar. Okay, here you go. The equation for the x and the equation for the y are similar. That's what x is, pi over 2 minus beta. Let's see what y is. Here you go. Beta and pi over 2, that must go to the other side. Okay. So, just like we got it before, pi over 2 minus beta. So the angles x and y, they are the same. But the angle y has an advantage. The angle y here has an advantage. Why is that? Because y, cosine of y is a divided by r. Okay, that's the advantage of the y. Cosine of y is equal to cosine. Here you go. Oops. Y equals to x equal to pi over 2 minus beta. And, you know, cosine of y equal to let's see here, a over r. A over r. Okay, why we are doing that? Because the x and y the components in the xy plane is going to cancel out. You're going to end up having only a b field along the z-axis. Okay, so my dB is z. Okay, here you go. Magnetic field will have only a z component. exponent given by dBz equal dB cosine of y, which is a over r. Oh, let's make sure it's cosine of y. Okay, yeah, cosine of y, which is a over r. And now it's just a matter of calculating the b and then integrating. Let's go get it. Here you go. dB is mu naught I over 4 pi okay, is that ds. Let's see, let's use the vectorial equation, right? Here you go. Okay, let's take a look again. ds and r. Here is ds, here is r. Okay, it's always perpendicular. Okay, you can see it's always it's at a different plane, but it's always the perpendicular. Okay, that's the, here you go. That's the direction tangent to the circle, and that's the radial direction to the circle. Okay, whether it's in the xy plane or above the xy plane, the angle doesn't change because we are talking about the axis of the loop. Okay, the angle here remains the same, 90 degrees. So what we end up having is, you know, is a ds. Those two are perpendicular to one another. R hat has magnitude 1, so all we have to do is to keep it ds. Okay? So what I'm going to do, I'm not going to put vectorial here. I'm going to put magnitude, okay? And now here I put the magnitude as well. Here you go. Now the r square cannot be the r cannot be replaced by a, because your r is going to change as you go higher and higher along the z-axis. We have to keep the r in there, and we integrate on the s. We integrate on the circle of the loop. Okay, so here you go. B mu naught I a d theta okay. Theta is independent of r. And when we integrate, here go, that should be dB. It still should be dB. Yeah, let me put the integral here. From 0 to 2 pi. Mu naught I for pi, because A is independent, because theta is independent of R. You don't have to integrate it. We end up only with the theta there inside the integral. Okay. Let's take a look at the solution. Yeah. Yeah, R square. I use the phi. Okay. Okay, so there is a little mistake here. Let me correct that. Let's see here. The dBz, okay, here you go. The dBz is dB cosine of theta, okay? Not this one here. Let me correct that for you. dBz is, here you go. That's what it is, okay? The dB is that thing here, okay? And now, what we have to do? We have to replace, here you go, like that. The dB right in here. And then take the integral, okay? And then take the integral. So let me erase that. I'm gonna fix that here. E over R. Cosine of I. Yeah, that's what I call the cosine of y. Let's see. Let's take a look here at the drawing. Drawing here. The theta. Y is this one. Yeah. Okay. Is the what I call the cosine, the y is in reality the theta. Okay. This one here is cosine of theta. And you can write that down in terms of z and a, okay? You know, you're going to integrate over the full circle, and you're going to be at 2 pi in there. You get something like that. Okay, so let's do that step by step. So it's always good to do that. Okay, here you go. Mu naught I for pi. This R combines with the other R, becomes R cube. Mu naught I for pi, A R cube. Okay, ds. The ds becomes a theta, a d theta. Okay, and here go, a becomes a square, and we end up with 2 pi. So almost there. Oops. 2 pi, 4 pi becomes 2. Okay, and what I did in the other derivation, I substitute the r by z square, square root of z square plus a square. Mu naught I square I over 2. Mu naught over, okay, so here you go. So the magnetic field decreases with the distance from the loop, but like again, I can here write that in terms of, here you go, a square plus z square power of 3.5. Okay, save it. One more. Okay, so here you go. This one is an interesting one as well. This one here that you see, an infinitely long wire. Okay, infinitely long wire. We can use the Biot-Savart law to calculate that. I'm not going to do that because there's an easier way of calculating this magnetic field as infinitely long wire, okay? So here you go. Let's just pencil out infinitely long wire along the x-axis. You want to calculate the magnetic field at a point along the y-axis. It doesn't have to be along the y-axis, it can be anywhere because this wire here is infinitely long. Okay, so here you go. And you get a ds. That's the vector ds to the right along the x hat. Here's the vector r from the ds to the point where you're calculating the magnetic field. That's the angle. Okay. The angle starts at 0 and ends at pi. Notice that it keeps on increasing. Okay. We're going to do the r cross ds cross r. That's going to be the direction of z. Okay, if you use at the other side, the direction is going to be into the board, minus z. And what you have a magnetic field that circulates around the wire. The magnetic field always circulates around the wire. Okay? And we can solve this problem, you know. Here you go. That's how it goes. The magnetic field circulates. Now we have the wire looking along the x-axis. Okay? Here you go. See that? X, Y, Z is coming out of the page. If you look directly into the x-axis, you know, you can map the magnetic field around this wire. It's going to circulate. Okay, that's how the magnetic field looks like. As you go further and further away, you know, the magnetic field, the magnitude of the magnetic field decreases. So what do you get the final formula for this problem? For an infinitely long wire, the magnetic field will be given by, you know, mu naught I over 2 pi r. Let's see here. No, it's not 2 pi I. It's 2 r. Mu naught I over 2 r. Here we go, this one here that I want. Yeah, 2 pi r, that's right, just like I said. 2 pi r, initially said 2 pi r. But like I said, I'm not going to do that here because this one is very lengthy. Why is that? Because there's a simpler way of solving this problem using Ampere's law, okay? We use the integral form. 6:38 right now. We have 10 more minutes to go. Now, okay, we can also calculate the magnetic field due to 2 wires, I1 and I2, the net field. Let's see that's what I want. No. Okay, here we go. Okay, so magnetic force between 2 current carrying parallel conductors. Okay, so this current produces a magnetic field that's going to interact with this current, with this other current wire. Okay, a magnetic field applied to a current carrying wire generates a magnetic force. Okay, the magnetic field just is easy, a very good rule of thumb to determine the direction of the current in a wire is to use the right hand rule. Okay, if the current is pointing upwards, you just make your hand move in a circular fashion with the thumb pointing the direction of the wire. So in this case, the magnetic field will circulate in this direction here. Okay, that's a very, so in this case here, the magnetic field is going to point into the board here at this spot, and the magnetic field of this one is going to point out of the board in this wire. You go ahead and do the I cross B, and you're going to see a force, a magnetic force to the right. Okay, and you do for the other wire, you see a magnetic force to the left. So if you have, what does it mean? It means that if you have 2 current carrying wires carrying a current in the same direction, they're going to have an attractive magnetic force. If we invert the current, then the force is going to be repulsive. That's okay, and those 2 forces are supposed to be the same because those 2 same magnitude, right? Because you have 2 interacting objects, and you apply Newton's third law. Newton's third law works at the magnetic for the magnetic field as well. Okay, so let's stop here now. 6:41, and do you have any questions? You must be worried about the exam now, right? For the Tuesday. Yeah. Okay, so you folks did pretty well in the first exam. Most of you did pretty well. I could see that. I saw their grades. So I have every reason to believe that you're going to do well in the second exam as well. Yeah. Check the date. Check the date. I believe I put the date for the exam, or the exam is gonna check. I changed it here in the classroom last time, right? I don't remember the exact date. I believe I put after the exam. I believe I put a deadline for the 28th. Maybe I don't remember. Okay, the exam is gonna be at 26. Okay. And okay, any more questions? Good. So I see you next time. We finish this chapter and then we do the exam.